My name is Maxim. I'm a co-founder and a co-CEO of Enlightra. We develop photonic solutions for fast and energy-efficient optical interconnects. And as you can guess, optical interconnects, optical connectivity of AI cluster is one of the biggest opportunities for us in terms of the market. So today I'm going to speak about one technology which is kind of a core piece of our tech stack, which is a special type of lasers called comb lasers. And I will tell you why we believe they will be driving optical interconnects in the AI clusters in the next decade. First, well, what is the comb laser? Well, if you like me, who spent the big part of their career in science, and you most probably know more scientific term of these devices, which is optical frequency combs. In essence, they're it's a very simple device. It's the laser which shines at not on a single color frequency, but at multiple frequencies, and it has two distinctive features. First, the spacing between the laser lines which it produces is equidistant, and second, it has a high coherence, individual coherence of the lines, and also high mutual coherence of the lines. And since 2005, actually in 2005, it was awarded with a Nobel Prize, and since then it already took some niches on the market. They are more kind of scientific oriented niches, and they are frequency metrology, fundamental science, applications in the generation of low noise microwaves, and also spectroscopy. But due to, well, there is one problem with the comb lasers, and the problem is that they're quite bulky and complex, and at least in their conventional representation. And there is a set of more interesting fields with much stronger market potential, such as well, optical communications, optical interconnects, LiDAR, and many others, who unfortunately cannot really use this technology. And that was a big drive in the past decade to develop a chip-scale implementation of these lasers. That's just, as I call them, chip-scale comb lasers. And this is devices which potentially should have a low size, weight, and power. They should have a very good compatibility with the mass manufacturing. And finally, they should be aligned with the standards. And by standards here, I mean the standards, kind of the communication standards, for example, the compatibility with the ITU grid. So the comb laser spacing should be aligned with 100, 200, DWDM and CWDM spacings used in the communication networks. Well, now we know what the chip-scale comb lasers are, and but why they're interesting for the optical interconnects? Well, the answer here is you probably heard many times today. These are LLMs, and with their onset and with their very resource-intensive training and also their demand for the low latencies, the bandwidth, the demand for the bandwidth, the need for bandwidth is inside these data clusters, AI clusters, is growing very fast. And well, you probably heard from Google and NVIDIA and others that the AI workload grows 10x per year, and it's not just a 10x, it's like a real 10x, which the market and which the industry has to deal with. And the problem is that the only way to address this need and the only way to go to sustain this future trends of these 10x over 2 years, several years, you have to switch to optics. So you have to go from copper to optics, and there is mainly two reasons behind it. First is that, well, first, optics, using optics, you can rely on wavelengths divisional multiplexing, so you can use multiple wavelengths, multiple lambdas in a single fiber in contrast to copper. And second, which already was mentioned earlier in the session, that if we are talking about longer distances, then the optics and fibers are much better in terms of the energy efficiency. And well, with optics comes another problem, that you need lasers. And if you would like to drive all these, say, WDM links with a single color laser, then you're probably facing several issues. One issue is the manufacturability, then yield, and then you need to assemble all these lasers all together. And then eventually the yield of the final device will be quite low. So what's the solution? Well, the solution is the comb lasers, because they can shine at multiple frequencies, so you need only one device to do this. They can cover very broad band, like 8, 16, even more lambdas from a single device. They are compatible with the high volume manufacturing, and finally they can they're much easier in terms of assembly, because you don't need to assemble 16 lasers together on a single die. And this is what we are doing at Enlightra. So using our proprietary comb laser technology, we develop foundations for fast and energy efficient optical interconnects. So the company has been established in 2022, and since then we grew from 3 people to 20 people. And actually, that's the slide. It's already, we're growing that fast that the slide is already outdated. And more than half of the team is actually have PhDs, and they also have very good experience from top tech companies. We are doing very state-of-the-art R&D not only inside the company but also with our tier 1 partners, which we finance by a few grants from the EU and also US. So we work with DARPA, for example, recently. And also we are very proud to be backed and supported by world's famous startup accelerator, Y Combinator, and we also were recently we were part of Intel Ignite corporate accelerator for startups, which I could highly recommend here. I have a couple of slides on the technology very briefly, without going too deep. So what we are doing is that we are using very tiny integrated resonators, which can be manufactured on silicon-based chips. If you drive these resonators with a continuous wave, kind of off-the-shelf commercial laser, standard DVB laser, you can generate a comb lasers. Of course, you need to do some tricks with it. You need to know how to arrive in a specific operational regime, but eventually we succeeded in knowing how to do this. And once you're doing this, once you've done it, you can get a comb laser with very distinct spacings from 50 gigahertz, so it's DWDM compatible, all the way up to CWDM. We could have a very good coherence of the comb lines, so each line can go down to 1 kilohertz, and then we already showed that we can do these devices in high volumes, so we're working with high volume foundries. And then another kind of beauty of the technology is that we are merely band agnostic, so we can work in C band, we can work in O band, we can work in any other band you wish where you can find just a pump laser. Well, having a good technology is nice, but what we realized earlier in the company that it's much better to have a device which you can give in the hands of your customers, and this is what we've been doing since almost 1.5 years now. So we developed a tabletop comb laser based on our technology. So it's a fully turnkey device. So we shipped it at the beginning of the last year. It can have a different spacings from 100 gigahertz to 400 gigahertz, and we can go also beyond it. I think one of the biggest achievements of the company was that one of the customers we worked with so far, he tested internally the device for more than 2,000 hours, so it's 2.5 months non-stop operation, and we were quite excited to see that it was no failure operation during this time, and it was manually stopped. It didn't mean that the device broke. We also if you would like to use our technology integrated into your solution, we also offer, as we call, comb laser engines. So essentially, it's the package or butterfly package which has all the components inside to produce this comb laser. We again can offer here different spacings from 100 gigahertz to 400 and again beyond. These comb lasers, they feature very low phase noise, which I already mentioned, below 1 kilohertz line width, and we also did some reliability testing in our own thermal chambers in house. So we did during the operation we did the temperature swings from 10 to 60 degrees, and we also ran them for several hours. I think actually for 24 hours at 85 degrees C. So it's kind of a standard temperature for silicon, which you probably heard about. Well, in the past 2.5 years, we've been doing not only the comb lasers, we developed a lot of technologies around them also. So, and we built 3 kind of major pillars here. The first pillar is the portfolio of integrating photonic integrated components. It's some verified design blocks which we tested with our foundries. And we know how to simulate them, we know how to integrate them in bigger circuits and kind of have more functionality rather than just a comb laser. The second part is it's a dark art of photonics, which nobody is speaking about. So it's photonic packaging. Essentially, it's how to bring the light into the chip and off the chip. And we also gained some expertise here. So we developed our own packaging process for fiber to chip, laser to chip. We know how to do it such that it could handle high powers and also high temperature loads. And finally, the last pillar is integration. Everything, all of these chips and package chips into the systems, and which you can see on the right part of the slide. So we know how to make sure that these PICs, which are temperature sensitive sometimes, they can operate at, again, under different environmental conditions and operate stably, thermally and optically. On my last slide, call to action is a contact us. We'd be happy to talk to you if you are interested in our comb lasers. As a partner, if you'd like to buy it, we do also demo. We have a couple of demos which are now traveling, I would say, 24 days a month, so almost like 4/5 of each month. And I'm not sure if it's the right auditorium to have a call action, join the team, but if you're interested to join the team, let me know. Thank you.
Does anyone have any questions? We've got time.
I have a question regarding the pump laser. What is the power of pump laser? Because inherently you have a non-uniformity in the spectrum, and I see that you achieve a high power. So are you using some amplifiers? Because
for the pump lasers, for example, we're talking about here or here, the pump laser could be between 100 milliwatts and 200 milliwatts. This is what we can do. For this particular result, we used an additional amplifier. You're right, because plus 7 dBm per line.
Thank you. That was my understanding.
Yes. Maybe I didn't talk very carefully through this slide, so apologies about this.
Yeah, you said in your presentation that it will be very useful for data center application. Do you have already specific, are you thinking about LPO, CPO, or the application in terms of the integration?
I would say we are keeping our eyes open. So actually we, after talking to several customers, we even see the difference in their approach, how to use our technology. Some people are more interested in remote laser source devices, so for driving the kind of their silicon photonics. We have other customers who are interested in integrating, let's say, the resonator, which is creating actually the comp on their silicon photonic chips. So I would say that here we are trying to be as open as possible and let's say keep our.
Is it silicon or silicon nitride?
It's a silicon nitride. I'm simplifying here. It's a silicon chips, but many foundries they offer silicon nitride plus silicon fabrication process. Yeah.
It's better to say that it's silicon nitride.
Yes, it's a silicon nitride, exactly.
But it's your PDK, yes?
It's our PDK, that's right. It's our PDK, but it's not our fabrication process. So.
The Towerges, for example, they have silicon and silicon nitride.
Exactly, and some other foundries as well.
Yes, some other foundries.
Maxim, a quick question.
Yes.
You just happened to mention an amplifier, but you also hinted that you're going to put stuff in front of this cone laser. So are you looking at transmitters? Can you say anything in terms of what you're doing in terms of PIC?
In terms of PIC, so far we are mostly focused only on the comb laser, and in terms of the modulation, we would rely on our customers. But given that we will advance further in our development of our photonic technologies, then we also look into development of the modulating kind of modulation board. Again, since we have a silicon nitride plus silicon, it's quite easy way to integrate modulators together.
Another question, please, just because we've got a couple of minutes. In terms of the external laser source pluggable that's been developed, if you look at co-package optics, and again, we'll come on to this later, it's very early days, but people tend to use DR1 and FR4, so in other words, 4 wavelengths, 1 wavelength. Are you seeing anyone talk to you about looking at 8 wavelengths, 16 wavelengths?
We have actually, that's why I wanted to show this slide, and it's a pity that I didn't talk to. Actually, this is so why I wanted to show this particular spectrum, because it's a 16-line all-band comb with 200 gigahertz, and this is So we had a demo of this device running at OFC 1 month ago, and we have a lot of interest from the companies from big companies doing optical interconnects.
Okay, and a 30-second question going way off topic. So people are talking about coherent for long haul and eventually doing perhaps parallel designs. Is anyone talking to you about your cone laser for that?
Yes.
The smart said it all.
It's the next.